Thank you for having me back, and thank you all for coming. I know that it's pretty busy here, so thanks for making the time. So a couple of things first. I have lecture notes on my web page, so you just go to math.utah.edu/Hacon and follow the link to the lecture notes. So you don't need to take notes, they're all there. Well, I have 99 pages of lecture notes so far that should get me through at least 3 or 4 of these lectures. Well, usually I'm too ambitious, so maybe it'll be enough for all 5, we'll see. And another thing is feel free to interrupt at any point if you have questions, if something is not clear, if I make a mistake. And also if you want to discuss the material at some other time, my office is 351. And feel free to drop by and ask questions. Okay, so the topic of the lecture is the birational geometry of irregular varieties and generic vanishing theorems. So generic vanishing theorems are a very useful tool which, together with the Fourier-Mukai transform introduced by Mukai, allow us to get remarkably strong results about irregular varieties. So maybe first things first, what's an irregular variety? So for now, this will change at a certain point. Let's assume that X is a complex projective variety. And let's also assume, for simplicity, that it's smooth. Then we say that X is irregular if it has non-vanishing holomorphic one form. So X is irregular if H1 of O of X is non-zero, which of course is equivalent, since it's a complex projective variety, to H0 omega 1 of X being non-zero. So anytime you consider an irregular variety, there's an interesting map to an abelian variety associated to it. So the universal map to an abelian variety is known as the Albanese map. So let me denote by A from X to A. This is the Albanese map. Capitalize Albanese. So, well, I call it map, but it's always a morphism. It's always defined everywhere. And so how can you think of defining this map? So let's say that, let's look at the space of holomorphic one forms. So let's pick a basis, omega 1, omega g. So this is a basis. And let's also fix some base point on X. Then we can send any other point in X. We can just send it to integrating from a base point x0 to X, these various holomorphic one forms. So here, I guess by G, I'm denoting the dimension, which is going to be the same as H0 of omega 1 of X. And so since I'm taking these integrals along holomorphic one forms, I am getting something in, I guess, what would it be? Omega 1 of X dual. But these integrals are not well defined. They're only well defined up to closed loops. And so we have to quotient out by H1 of X Z. So this is a complex torus. And this is, any other map to a complex torus will factor through the Albanese map. So it's universal in that sense. Okay, and in terms of notation, let me set the dimension of the Albanese image of X. This will be known as the Albanese dimension of X. Of X, and I will say that X, the best case scenario, X has maximal Albanese dimension. I guess I'll abbreviate that as maximal Albanese dimension. Of course, if its Albanese dimension is actually equal to its dimension. Okay, and so I'm going to try to be making the case that the birational geometry of varieties of maximal Albanese dimension is extremely well understood. Okay, so maybe I'll start by giving a preview of some of the results that are known for varieties of maximal Albanese dimension. So if X has maximal Albanese dimension, then, well, several things are known. First thing, we know that X has a good minimal model. I believe this is due to Fujino, who observed that you can just run the relative minimal model for X over its Albanese variety, and the outcome is actually a minimal model for X itself. Another nice property, we understand the birational maps of the pluricanonical maps of X very well. So we know that the codary dimension of X is greater or equal to 0. This is not a difficult fact. You can just pull back holomorphic n form on A, where n is the dimension of X, to get a holomorphic n form on X, and hence a section of the canonical line bundle. So this is a triviality. However, when I look at the linear series defined by 4 times the canonical line bundle, or any higher multiple, then this defines the Ithaca federation. So if you don't remember what the Ithaca fibration is, let me do a particular case. If X is of general type, so I'll review these definitions later, but for example, if K of X is ample, that would be an example of a variety of general type, then 3 times the canonical line bundle gives you the Ithaca fibration. In this case, it gives you a birational map. So, you can't expect their geometry to be as simple as the geometry of curves, but it's maybe as simple as the geometry of surfaces, right? Because for surfaces, you have a fixed, pretty small multiple of the canonical line bundle that gives you the Ithaca fibration, or when it's of general type, it gives you birational map.
What did you say about the codary dimension bigger than or equal to 0? Because, like, suppose your curve is embedded into a Jacobian.
Mm-hmm.
Did you say pulling back the n form?
So I pull back a holomorphic 1 form in that case, and I get a non-zero holomorphic 1 form on the curve, which shows it's not P1.
That's fine.
And in general, you do 1 is replaced by the dimension.
Oh, that's okay.
Yeah, very good. Another observation is that the Euler characteristic of omega x is always greater or equal to 0. So, of course, I'm not saying that x is of general type, so you could not really expect strictly positive. So that's sort of similar to surfaces, right? The Euler characteristic of if x is a surface of general type, then the Euler characteristic is always strictly positive. This result, maybe I should mention who the results are due to. This one is due to Green and Lazarsfeld. The result above had contributions for several authors, but in this strongest form is due to, I think it's Jiang. Wait, let me make sure I have it correctly. Yes? Jiang, Lahot. I don't even know how to pronounce that one. This one I do, it's Italian, so Tirabassi is easy. Yeah, he's Spanish, right? Okay, so so where are we? Then the next result is quite sophisticated. So maybe I should use a new blackboard. So this here. So let's suppose that f from x to y is a surjective morphism with connected fiber of smooth varieties, so in particular f log star of OX is of y. If y is of maximal urbanicity dimension, so maybe I should, since I've said x is maximal urbanicity dimension up front, so let me call it y to x. If x is maximal urbanicity dimension, then the codaric dimension of y is greater or equal to the codaric dimension of x plus the codaric dimension of f, where f denotes a general fiber. So this is an instance of the famous CNM conjecture, which is a very difficult but very important conjecture in birational geometry, and this result is due to Cao Paon. And it's a very sophisticated result, and the proof, so far, the only known proof, uses analytic methods. Interesting, but somewhat difficult analytic methods. So maybe I should remind you what these symbols mean. So maybe I'll do it right here. What does the codaric dimension of x mean? Codaric dimension of x is assumed to be minus infinity if h0 of mkx, this is known as the M3 genera of x, is 0 for every m greater than 0. And otherwise, the codaric dimension is the maximum of the dimension of the image of x under multiples of the canonical line bundle, where m is greater than 0. And so the codaric dimension is always a number that is either minus infinity, 0, 1, all the way up to the dimension of x. And the case when it's equal to the dimension of x is known as the case of general type. So somehow this is saying that if you have lots of pluricanonical forms on x and on the general fiber, you can somehow construct lots of pluricanonical forms on y, right? Of course, if y were just a product of x and the fiber, it would be a trivial result, right? Somehow how these fibers fit together is interesting. And since I mentioned this particular case of the CNM conjecture, there's also another case due to Fujino. If f from, let's say, V to W, again, is an algebraic fiber space, a surjective morphism, so let's just write f log star over V is OW, and the general fiber is of maximal urbanicity dimension, then the codaric dimension of V is greater or equal to the codaric dimension of W plus the codaric dimension of the fiber. And this, if I remember correctly, is due to Fujino. Of course, once you know that the general fiber has a good minimal model, you can deduce it other ways. There's a result of Kawamata, but Fujino actually proved this before we knew that varieties of maximal urbanicity dimensions have good minimal model. Let's see if there are any. Maybe there are a couple more results that I would like to mention before I start talking about the techniques. So another result, so these are sort of general birational geometry results. There are also results that you can obtain which are very specific to the geometry of abelian varieties. So one natural question when you start thinking about abelian varieties is understanding the singularities of divisors on abelian varieties. One of the motivations for that is to understand their moduli space and understand, for example, the Jacobian locus inside the moduli space and things like that. So this is a small result in that direction, but nevertheless an interesting result. Suppose that I have a theta, a principally polarized abelian variety. So this means in particular that theta is an ample divisor and it only has one section. Any ample divisor in abelian variety always has sections. That's the smallest number of sections it could have, one-dimensional space. And let's assume that G is some divisor corresponding to a positive multiple of theta. Then the pair A1 over mg is log canonical. Now, if you don't know what log canonical means, well, I'll explain it later, but one consequence of being log canonical means that the multiplicity of, at any point of your abelian variety of this divisor G is bounded from above by m times G. By little g, I'm always denoting the dimension of the abelian variety A. And in fact, one can also show that if that equality is achieved, so this is a very precise theorem, if the multiplicity of G actually achieves mg, then A is splits as a product of elliptic curves. So these are elliptic curves, and the divisor G is just obtained by pulling back multiples of points on each component. So it's P1 upper star of M times a point, I don't know, E1, let's say, plus P2 upper star ME2 plus PG upper star MEG, right? So clearly this is one way to construct the divisor with that property, but it's the only way. So in fact, I guess if there is no factor like this, then you could say that the pair A1 over mg is KLT, if you know what that means. If you know what that means. So this result is due, the first part is due to Eiland-Lazarsfeld. And the second part is due to myself. Okay, so we can have very precise results on the birational geometry of abelian varieties. Another nice result is the following, that we'll see the proof of this, is, go ahead.
So H0 of OA theta is equal to 1.
That's my assumption.
That defines divisor. Yes?
Yes.
That is always smooth?
Theta divisor is always smooth? No, but they have mild singularities.
But then A and 1 over mg, so suppose I take this multiple section. So then 1 over mg will be that divisor, no?
No. So this linear series here has lots of degrees of freedom, right? So the A0 over m theta, what is it? I think it's just maybe m to the g.
So this g is some general member? Or
No. A general member will be smooth, right? Because
So, yeah,
3 theta is very ample already.
so
But
then any member, yeah?
any member, yes.
So again, I repeat the question.
So you could pick m theta if you want.
That's right.
Right, so if you pick m theta, then the m's cancel. What this is saying is that the pair A theta is log canonical. So it says that theta itself has mild singularities. We can be more precise, something like the second part that I said. But
You're right. Sorry. Yes.
so, yeah. So if the dimension is 2, pretty much, it's either a smooth curve or it's a sum of 2 elliptic curves, essentially.
Sorry.
No problem. Gives me a chance to slow down and people to think if they have other questions. Okay, so what was the other theorem I want to say? Let's assume that we know that the Amperigena, we have a variety, let's call it y. The Amperigena of y is 1. Then, for any sum m greater or equal to 2, then the Albanese map of y is surjective. So this in particular implies that the dimension of A, which is h1 of O of y, is less or equal to the dimension of y. we have equality, then this map A, then A from Y to A is birational. So this is known as a birational characterization of abelian varieties in terms of just two birational invariants. The plurigenera, any, say, P2 of Y, and the irregularity, H1 of O of Y. So
you assume that Y has maximal Albanese dimension?
No, I don't. So the map will be surjective. Now, once I assume that the dimension is the same, I have a surjective map between varieties of the same dimension, so then it has to be maximal Albanese dimension. Right? So this surjectivity plus this assumption gives me maximal Albanese dimension. And then the trick is to show that it's unramified somehow. So it has to be in a tau cover birational. And we'll go over the proof of that. And there are other precise results. Maybe I won't write them all down. So there's a result of Pareski that says that the syzygies of a principally polarized abelian variety are precisely understood. A remarkably strong result of Pareski. And so these techniques that I'm going to talk about apply to a whole bunch of interesting results related to abelian varieties or varieties with non-trivial maps to abelian varieties. Maybe the last comment I'll make is, so far I stated everything for complex projective varieties, but as we're going to see, actually one can generalize a lot of these results to positive characteristic by using
No, I don't understand this statement.
Okay.
So PMY is equal to 1.
Yes.
I see. Now I understand. Sorry.
No problem. So what was I going to say? Oh, okay. So let me just say similar results sometimes hold in positive characteristic. And the methods that we use, of course, involve the theory of F singularities. So we look at the Frobenius acting on the canonical line bundle and the trace map. And that gives you some interesting results. So let me just say, using theory of F singularities. And so the ideas from F singularities make a very natural appearance once one frames the questions in the right way. Okay, so this is just the motivation part. And so the next step, the next part that I would like to talk about is vanishing theorems, because one of the main tools that we're going to use is generic vanishing theorems. And of course, you can't really talk about generic vanishing without knowing about vanishing theorems. And vanishing theorems play a fundamental role in higher dimensional birational geometry. So before I move on to vanishing theorems, any questions?
Like, can you give me just one example of the first statement of number 7? PMY is equal to 1, and then other than elliptic curves.
PMY, so
is equal to 1, and the Albanese map is surjective.
Is surjective?
Yeah, that's what it says, yes?
Okay, so
not elliptic curve.
well, I mean, so
Not
okay, so I take degree 2 cover of an elliptic curve, right? But then you're not expecting the plurigenera to be 1 anymore,
yes.
right? So of course, you know, given any abelian variety, you can construct many finite covers. Just pick an ample divisor and just construct a corresponding cyclic cover. So that's one kind of example.
But then PMY might be bigger than or equal.
Theorem says it has to be bigger.
PMY is equal to 1, no?
If it's equal to 1, and then the map, Albanese map is surjective, and moreover, if the dimensions match, then it's actually it's actually equal to your abelian variety.
Sure.
So
my question was.
So if it's not equal to the abelian variety, then the PMs tend to be higher, right? So each.
My question was PMY is equal to 1 for some m, and the Albanese
Again, I don't know. How about you pick a divisor D? You're going to have to give me some reason why you don't like this example, okay? Then maybe I understand. So we pick a divisor, a general divisor in m theta for m greater or equal to 3, so it's very ample. And then you take the cyclic cover y to a, which, corresponding to spec of the direct sum of O minus I theta, I equal to 0 to m minus 1. This is the cyclic m-fold cover, and this cover will certainly have Pm greater than 1, and it's a generically finite cover of an abelian variety.
No, it's equal to 1.
Oh, well, okay, so that's going to be hard, right? They are few and far apart, these examples.
Yeah.
Okay, I can give you an example which I was going to give you later on, which is less trivial. So some kind of...
So just ignore me. If it's difficult, then I would be happy.
Oh, no, it's not particularly difficult, but so one thing that you are a little disappointed by this is that it has Hartley genera, right? So in particular, the Euler characteristic of omega y is strictly positive. So let me give you an example, a more interesting example of a cover of a abelian variety, which I was planning on giving you later on. I'll just give it now and then. Okay, so I'm going to construct, this example I'm going to construct is from x to a. It's a z to z squared cover. And it has the interesting feature that the Euler characteristic of omega x will be 0, but x is going to be of general type. Okay, so this is somewhat interesting, right? Because later on we'll prove that the Euler, if it's of general type, well, regardless, the Euler characteristic is always greater or equal to 0. By analogy with surfaces, you may hope, and in fact Collard had conjecture, that the Euler characteristics should be strictly positive. So this is a counterexample to that conjectural collide. So first of all, I'm going to pick A to be the product of 3 elliptic curves. I have to go to a dimension at least 3, because for surfaces, it's a theorem that the Euler characteristic is strictly positive. Okay, now I'm going to pick a bi-double cover of each one of these elliptic curves, and then from that I'll construct a bi-double cover of A, which will be sort of quotienting by some diagonal action. Let's be a teeny bit patient. So let me pick Pi on each elliptic curve such that Pi to the tensor 2 is isomorphic to OEI. So for each elliptic curve, this defines a degree 2 étale cover by taking the corresponding trivialization, the square root of the identity in it. Okay, and then I'm also going to pick ample line bundles, Li, and maybe these will have, you can pick them of any degree you want, but we might as well assume that degree Li is 1, and then you take the second tensor power of these, and you pick some reduced divisor, Di, so we want this to be reduced. Why do I want it to be reduced? So that when I take the corresponding double cover, it's smooth. It's normal, and in particular, it has to be smooth. Okay? So for each one of these, I have, this defines a twofold cover of each EI, another twofold cover, so a Z2 times Z2 squared cover. Okay, now I can use this. If I use this data, I get some cover, let's call it X tilde, to A of degree, now I'm going to get the degree one wrong, 4 cubed, so a Z mod 2Z to the 6 cover, right? Because on each factor, I have a Z2 squared. And then I'm going to take the quotient of this cover. So now I have a very big abelian group. And I'm going to take the quotient of this by an appropriate, and I don't remember off the top of my head exactly what this appropriate Z mod 2Z to the 4th group looks like to get X. So let me describe X explicitly to you now. I'll describe it just like we described this cover as spec of a certain O algebra. Let me tell you what the O algebra here is. And if I get into trouble, I'll just look at my notes. But it's several pages ahead, so it's better if I get it right. So if this map is, say, A, I want A lower star of O of X. That should be, well, it should be O of E1 times E2 times E3. Of course, right? We're not going to, we have to have that. Then I would like it to have terms that look like this. L1 box times P2 box times OE3 direct sum OE1 box times L2 box times P3 direct sum where is it? P1 box times I lost my train of thought. What is it?
Oh, that's okay.
Well, okay, I went this far. I should OE2, okay, box times L3. Okay, so the fact that it's of general type is now sort of almost apparent because you sort of, the pullback of an ample line bundle from each of the three factors makes its appearance in here. These are duals here. So the pullback of an ample line bundle plays a role on each factor, so you really would expect it to be of general type. I slightly lied. This one is not smooth. It has canonical singularities. They're clearly quotient singularities, and you can check in local coordinates what they look like. And you see, when you compute H0 of this guy, okay, so you probably want to compute H0 of A low star of omega x. That's just going to correspond to the dual of this guy. None of these guys give a contribution because when you compute H0 of a non-trivial line bundle of degree 0 on an elliptic curve, that gives you 0 always. So these guys don't give a contribution. The only contribution you get is from this guy, right? So this is going to be 1. And it's an easy example to see that the Euler characteristic will actually be 0. So for example, if you compute HI of A lower star of omega x, tensor Q1 plus Q2 plus Q3, as long as these guys are different from P1, P2, and P3, this will tend to be 0 for every I. So let's just say for general Qi. So in particular, the Euler characteristic, which is a deformation invariant, is going to be 0. So this says that the Euler characteristic of omega x is the same as the Euler characteristic of A lower star of omega x because it's a finite map. That's the same as the Euler characteristic of A lower star of omega x tensor Q1 plus Q2 plus Q3, which I just established as 0. So there do exist threefolds of maximal Albanese dimension whose canonical line bundle is positive. It's of general type, but it's not as positive as you might expect from like a surface kind of situation. Right, so here, P1 is 1. And so now I don't remember the details on which pluricanonical map becomes birational, but I do remember that. So Jiang Lahos, I can't pronounce it, Lahos and Tirabassi proved this optimal result. Part of proving it, yeah, you can give me a course later. Apart from proving that this maps gives you the eta fibration, they also have to come up with an example where 3k of x does not give you the eta fibration. And, well, it's not this example, but it has a somewhat similar flavor. It can't be this example because that's of general type, right? But it has a somewhat similar flavor.
Thank you very much.
Okay, so keep this example in mind. When we talk about the cohomological support loci, this will be sort of an interesting example because whatever these cohomological support loci are, they are interesting in this case. So I'll come back to it. Okay, so now let's move on toward in the direction of vanishing. I'll try not to spend too much time on on actual vanishing theorems because most of you are probably familiar with them, but I sort of need to set the stage. For one reason, I'll definitely be using vanishing theorems. Another reason why I'm interested in introducing them is that you can think of generic vanishing theorems somehow as a limit of vanishing theorems. I'll make that more precise. And so in order to understand generic vanishing theorems, you need to understand vanishing theorems. And some of the tricks that you use in discussing vanishing theorems actually will play a role. So let me, of course, remind you, okay, maybe I won't do cell vanishing. Kodara vanishing, of course, you all know. It says that if X is a smooth complex projective variety and L is an ample line bundle, then we have vanishing of higher cohomology of omega X tensor L for any I greater than 0. So this is old news. It dates back to 1953, I believe. It's a beautiful theorem, but one of the disadvantages is that this condition of being ample is not well behaved from the birational point of view. Well behaved birationally. So what do I mean by that? So suppose that f from x prime to x is a birational morphism, proper projective birational morphism of projective varieties, then and L ample, then the pullback of L is ample if and only if f is the identity, right? An isomorphism. I'm assuming that these are smooth varieties, right? Because as soon as there's a curve that's being contracted by this map, then the pullback of L will intersect that curve 0, so it can't be ample, right? So ampleness is not well behaved. As soon as you have a non-trivial birational map, pulling back an ample line bundle is no longer ample. That property is destroyed. So the birational version of this property is L being Neff and big is better behaved. So for completeness, probably almost all of you know what this means, but L being Neff, this just means that the intersection with any curve, so you can think of this just as the degree of your line bundle restricted to the curve, this is always non-negative. And being big, well, being big is that the Kodara dimension of L is equal to the dimension of X. So one way of thinking of it is that the number of sections of multiples of L behaves like a polynomial of degree equal to the dimension of X. But in the case of a Neff line bundle, for Neff line bundles being Neff and big, it's the same as requiring that the top self-intersection, so let's call that dimension of X, of L is strictly positive. Okay, so the point is that then if I consider any birational morphism, if L is Neff and big, F upper star of L is also Neff and big. This is an immediate consequence of the projection form. Okay, so being Neff and big is a property that's well behaved for birational morphisms, and so of course in birational geometry it's much more useful to have a vanishing theorem stated for Neff and big line bundles. So that is Kawamata-Viehweg's theorem. So if L is Neff and big, let's say on a smooth complex projective variety, then higher cohomologies vanish. Okay, so this is very useful, and maybe one can remind you of one, even though most of you have probably seen it, I can remind you in one way that this is particularly useful. For example, you can very quickly recover from this Grauert-Riemann-Schneider vanishing. So what does Grauert-Riemann-Schneider vanishing say? So in this case, there'll be no ample line bundle, but we have F, let's say from X to Y, a birational projective morphism. And as usual, let's assume that x is smooth, but y could actually be quite singular. Then it's birational. The higher direct images of omega x are 0 for every I greater than 0. So I guess a fancy way of stating that, and I state it in these terms because that will be the way I'll state a lot of other results, is just to say that if I consider the element of the derived category corresponding to pushing forward, the derived push forward of omega x, then this is a sheaf in degree 0. Let me just write it as. So I often just say that's a sheaf. So a priori, it's an element of the derived category. It's a complex, if you will, and the cohomologies of that complex recover the high direct images of omega x, but all but the zeroth cohomologies vanish. Okay, so I'm gonna show you why well, how Kawamata-Vivek vanishing immediately implies Riemann-Schneider vanishing, and how in a certain sense they are actually almost equivalent. So it's a very quick argument, so I know a lot of you have seen it before, but indulge me for a second. So how do I want to think of doing this proof? A similar proof will appear later on, and so it's good to have this, to see this one right now. So the way I want to prove this is I want to fix L on Y sufficiently ample. And in particular, of course, f upper star of L is going to be nef and big. How ample do I want to assume that I fix this L? So I want to fix it so ample that when I look at high direct images of omega x, I'm trying to show that these vanish, but these are just some coherent sheaf. If L is sufficiently ample by Serre vanishing and Serre's theorems, then this will be generated by global sections. So in particular, if this is a non-zero sheaf, then it has lots of sections. And higher cohomologies right? So I can guarantee that higher cohomologies vanish, and the sheaf themselves are generated by global sections. Okay, but then notice that I can now try to compute the cohomology groups of omega x tensor the pullback of L. Now, on one hand, let's do this for I greater than 0. If I is greater than 0, I look at this cohomology group. Maybe it doesn't matter. For I greater than 0, I know that these vanish. The reason for this vanishing is Kawamata-Vivek vanishing. Right? On the other hand, I've arranged that all cohomologies of high direct images vanish. So by the obvious spectral sequence argument, so this is degeneration of the spectral sequence. Let me just say spectral sequence argument. You know that these cohomology groups will actually match H0 of Ri F lower star omega x tensor L. So I guess I've used this degeneration of the spectral sequence, and I've used the projection formula to say that when I push forward omega x tensor the pullback of L, L just comes out. Okay, so that's the projection formula as well. Okay, so these vanish, but I notice that these are generated by global sections. So this actually tells me that if something which is generated by global sections has no sections, then it must be the zero sheaf. But now L is a line bundle, it's invertible, so knowing that this vanish actually says, of course, that Ri F low star of omega x is equal to 0. Okay, and if you phrase it right, you could sort of go back, but let me not worry about that. So the thing, it's a relatively easy argument that I'm sure you've probably all seen before, But the point I want to make is we've applied this for the functor push forward for a birational morphism, but you could apply it to other functors. It's not done very often, but sometimes it can yield other really nice results. So we're going to do this with the Fourier-Mukai functor. We'll do the same kind of process with a little bit more care, and generic vanishing will fall out of that. So I'll make that precise in a little while. So, of course, if you know about vanishing theorems, you know that this is not the end of the story. Unluckily, Kawamata-Vivek vanishing is more flexible than Kodara vanishing, but stated in that form, it's still not flexible enough. So,
I'm sorry, Chris.
Yes?
Did you say generic vanishing follows from using Kawamata-Vivek vanishing in a clever way, combined with Mukai, Fourier-Mukai? Or did I misunderstand?
Correct. Okay. But, you know, of course, it's not quite, there's going to be some push forward with some maps, so maybe it's not Kodara vanishing, maybe it's Kolar vanishing. So I will now need to state some more powerful versions of Kawamata-Vivek vanishing that I'll then use with the Fourier-Mukai transform, and that just automatically gives you some kind of limiting procedure. So generic vanishing, which I have not stated yet, you want to look at statements like this without an ample line bundle. Just forget about that at all. Of course, you get a slightly weaker statement. You get some generic statement, not the actual vanishing statement. So the idea is we want to make this ample line bundle go to 0 somehow. Whatever that means, I'll make that precise. And then we'll get this statement. So yeah, U will be revealed probably by next lecture. We'll get there. OK, so I do want to state the more useful versions of vanishing theorems that I need. Of course, you all know that we could go on talking for days about vanishing theorems, so I'll try to make it brief. So there's a version that applies to of Kawamata-Vivek vanishing that applies to Kawamata log terminal pairs. So let me state that version. Probably I won't state the most general version, but I don't need the most general version. So, I'll call this Kawamata-Vivek vanishing 2. So in this situation, I want to consider XB is going to be a KLT pair. So I should remind you what KLT pair means. So what does KLT pair mean? So XB is KLT. So we want several things to be true. We want X to be normal. B has to be an R divisor, an effective R divisor. We want that Kx plus B is R Cartier. So you can write it as an R linear combination of Cartier divisors. And the nice thing about Cartier divisor is that you can intersect it with anything, with any curve that you want. You know, it's just, the intersection number is just restrict that line bundle to the curve, take the degree, and you can pull back via any morphism, right? You have a line bundle, pull it back by the morphism. And since this is a formal linear combination of line bundles, you can pull this back to it. So what you do is you pick a log resolution. So again, one needs to be slightly precise about what you mean about log resolutions. I want to assume that the exceptional locus of mu is a divisor. And I want to assume that when I look at the exceptional locus of mu, and I take the strict transform of B, this has simple normal crossings. And of course, I want to assume that X prime is smooth, right? I'm not going to write that. If it's a resolution, X prime better be smooth. Okay, so we have a resolution where, moreover, the exceptional locus is a divisor, and every divisor inside has simple normal crossing. Then we write Kx prime plus B prime as the pullback of Kx plus B. So of course, you have to pick a canonical bundle upstairs which is compatible with the canonical bundle downstairs. Canonical bundle is not unique, but you can always pick a canonical bundle upstairs such that its push forward matches the canonical bundle downstairs. Okay, so with that choice, this divisor B prime is uniquely defined. And so what we want is that one quick way of writing it, this KLT condition boils down to the round down of B prime being less or equal to 0. In other words, it means that the coefficients of B prime are always strictly less than 1. Right? So you don't, it's a usual thing when you're trying to integrate something, when you get to 1 over x, you have a problem. The integral is not going to converge, right? So you don't want to actually acquire a pole of order 1. That's the threshold. So if you don't like this, just think of the case where it's already log smooth. So x is smooth, and b is a simple normal crossing divisor. All of the coefficients are strictly less than 1. So it's some fractional divisor. Okay? So that you won't lose much if that's what you think of Kawamata log terminal pairs as being, because up to some birational morphism, that's what they are. Okay, so we have a KLT pair, and we have a line bundle, which is numerically equivalent to kx plus b plus m, where m is a Neff and Bldg R-Cartier divisor. Then higher cohomologies of L vanish. Yes?
Should we read that x is projective, or cos projective?
Yeah, of course. So in this formulation, I'm of course assuming x is projective. You can do more general, you can consider more general situations. I guess the following should be okay. So you have x to y, a projective morphism. And then in this case, you would say that Ri f lower star of L is equal to 0 for any I greater than 0. Right, so there is a, yeah, but I do want to assume that it's projective. So I want to say, I don't, it takes too long to make every statement in the relative situation, but pretty much every statement I'll make works in a relative setting and can be easily deduced from the projective setting. And so for the sake of these vanishing terms, I'm always assuming that x is projective. I write it this way. Other questions? Okay, so so you'd think that this is it, but actually there's two more statements I want to make. The next generalization I want to discuss is what you do if the pair is not Kawamata log terminal. Well, you can pretty much do the same thing, but you don't get vanishing on the nose. You need to make some adjustment due to the fact that the pair is not Kawamata log terminal. You need to take the multiplier ideal sheaf into consideration. So let's write that down. If xb is not KLT, we consider the multiplier ideal sheaves and nadir vanishing. And then the corresponding vanishing is known as nadir vanishing. So let me quickly define what multiplier ideal sheaves are. So I think the best thing is to assume that x is smooth. And we consider mu from x prime to x log resolution of the pair xb. And then we are going to define the multiplier ideal sheaf essentially by looking at this gadget. So the multiplier ideal sheaf, usually denoted by J of B, is given by pushing forward Ox prime K x prime over x minus the round down of the pullback of B. Okay, so first of all, one observation is that this is contained in the push forward of O x prime k x prime over x, where since I assume that x is smooth, this is an effective and exceptional divisor, so this is in fact equal to O of x. So this multiply ideal sheaf that I have defined is in fact an ideal sheaf. It's always contained in O of x. So it's an ideal sheaf, and the definition is independent. There's a small check to do. It's independent of the resolution. The other thing to observe is, so this gadget kx prime over x minus the pullback of B, if you look at what we wrote up there, that is, this gadget here is essentially the same as minus B prime as the roundup of minus B prime. Round up or round down? Yes, the roundup of minus B prime. So you see, if the coefficients of B prime are less than 1, then the coefficients of minus B prime are greater than minus 1. So when I round them up, they're greater than 0. So this tells you that the multiply ideal sheaf of B is trivial if and only if the pair XB is Kawamata log terminal. You're just using this formula here and then looking at the coefficients. So, of course, if you've never seen this before, you have to play around with it a bit, multiply ideal sheaves. You know, when it's a simple normal crossing divisor, all they do is they're taking the round. You don't need to take a log resolution. All you're doing is you're taking the round down of B. You're considering the components of B with coefficients greater than 1. But if it's not a simple normal crossing divisor, for example, if it's a cusp and you pick coefficients 5, 6, then the multiply ideal sheaf of a cusp with coefficient 5, 6 is the maximum ideal of the origin inside of OC2. And in fact, if the coefficient is less than 5, 6, it will be just OC2, and if it's greater than 5, 6, it's always non-trivial. So you think of this multiply ideal sheaf as a correction term that accounts for the fact that the pair is not Kawamata log terminal. And then you have the following Nader vanishing. So Nader vanishing, we're going to pretty much take the hypothesis of Kawamata Vivek vanishing, and we're going to throw away the property that XB is KLT. So I'll just rewrite it in a slightly different form. Let's assume that L minus KX minus B is Nef and big. Right? Above I call that M, and I'm requiring that that's Nef and big. Then this tells me that higher homologies of L tensored with the multiply ideal sheaf of B are equal to 0 for every I greater than 0. All of these higher homologies vanish. Okay, now in fact, the proof, maybe it's in the notes, maybe I won't do it now, but I should remark that Nader vanishing is an easy consequence in this form, is a corollary of Kawamata Vivek vanishing. Okay, so all you do is you go to a log resolution, because that's how you define this multiply ideal sheaf, and you set things up so that on the log resolution you can apply Kawamata Vivek vanishing to some sheaf, and all high direct images of the sheaf will be 0 by the relative version, so this global vanishing just follows from the global vanishing upstairs. I'm happy to go through the detail, but I need at least one person to ask for it. Maybe not. Okay, great. So we'll move on. So, okay, so I'm nearly done with the vanishing results. The last result I want to mention will also play a role for us, and this is known as collar vanishing, and dates back to around 1986. So probably Janusz's first big result, as far as I'm aware of. So what do we have here? We have a surjective morphism of projective varieties. And I'm going to assume that X is smooth, but Y doesn't have to be smooth. Maybe it doesn't even have to be normal. You can assume it's normal. You don't lose anything. So let's assume that X is smooth. Then, what do we have? We have several things. So first of all, if I look at these sheaves, Ri, F low star of omega x, they're always torsion-free. Of course, if you put I equals 0, the push forward of omega x is torsion-free. So the push forward is torsion-free. You get no points for proving that. But high direct images, it's a non-trivial result. The second result is that if I look at the push forward of omega x in the derived category, so think of this as a complex whose cohomologies give you the high direct images, then actually this splits as a sum, I equals 0 to k of Ri f lower star of omega x, where k is, we know what k is. K is the dimension of x minus the dimension of y. It can't be bigger than that, because for any value bigger than that, this sheaf would automatically have to be torsion, but the previous point says it's torsion-free, so it has to be 0. Right? So I don't really have to put k there. That follows immediately from here that the biggest value of I that you can consider is the relative dimension. Okay, so if you're not used to thinking of things in terms of the derived category, maybe you don't like this very much, but one consequence is, for example, that if you take cohomology of...
This equality is in what sense?
In the derived category.
You need some shift on the right.
Of course I need some shift. Yes, otherwise. Okay, so for example, when you go and compute cohomology groups for this, there's a spectral sequence that you do. So you take the cohomologies of this, which are the RIF lower stars, you take their cohomology as sheaves, and then you have to look at higher differentials. The fact that it splits as a direct sum means that there are no higher differentials. Right, so in particular, H K of, no, not K, L of omega x is the same as HL of this complex. I did nothing here, right? Because compute this cohomology, we're just pushing forward to the structure to the point. So here I can view it as push forward to x, to y, and then push forward to a point. It's the same thing. But then here's the interesting thing is that since this splits at this direct sum, this is equal to the sum of HL minus I, Ri, F lower star of omega x. And of course, this shift is what, aligns everything in the right degree. So shift by minus I just means take this sheaf and consider it as a complex, which is 0, 0, 0, until you get this sheaf in the ith position and then 0 everywhere else. Okay, so for any derived functor that you apply to this object, you get the same thing as applying it individually to these guys and then just summing the answer up. Right, so somehow you can separate variables. Okay, and I advertised it as a vanishing theorem, and there's no vanishing yet, so let's fix that. If I look at higher cohomologies of the push forward sheaves of omega x twisted by L, these are always equal to 0 whenever L is greater than 0 and L is Nathan big. So now we have a vanishing theorem. So in other words, higher direct images of a canonical line bundle behave like a canonical line bundle in their own right. Okay? So we have vanishing for them, and later on we'll have generic vanishing for them. Okay, so any questions before I move on to the next section? Okay, so I have a question for you. Another lecture is 2.5 hours. Am I supposed to take a break at a certain point or go straight?
Break.
So is now a good time to take a quick break?
Yes.
Okay, how long should it be? I have no clue what the custom is. 10 minutes, 15 minutes, what's the?
10 minutes. 10 minutes.
Okay, 10 minutes and it'll be a bit longer anyhow, so.
And if anyone has questions, feel free to.
Is talk about the generic vanishing theorems of Green and Lazarsfeld and sort of give you a little bit of an idea of how the old school results work. And before I can do that, I need to tell you a few words about topologically trivial line bundles and the Poincaré line bundle. So I'll do that in a second. I left this statement up because I just wanted to emphasize that similar statements also work when you consider, for example, Kawamata log terminal pairs, etc. Something similar to Kawamata-Vivek vanishing. For the sake of time, I don't want to write the most general statement. If we need to use it, I'll tell you exactly what the statement we need. So let's go back to talking about topologically trivial line bundles. So I want to talk about pick 0 of x. So just to quickly remind you, there's this short exact sequence, exponential sequence. So x is a smooth complex projective variety, e to the 2 pi I, and kernel is z. So then, of course, you know that line bundles correspond to h1 ox star. So this is pick of x. And there's a map from here to h2 xz. So think of it as picking out the degree of some sort. And then you can look at the kernel of this map is going to correspond to h1 of O of x modulo h1 of x z. So this group here is going to be pick 0 of x. So one line bundle that clearly is in here is the trivial line bundle, and every other line bundle parameterized by pick 0 of x is a topologically trivial line bundle. It's a deformation of the trivial line bundle.
Sorry, I'm a pain.
No.
Number 3 of polar vanishing.
Oh.
If I assume number 1 and number 2 is a corollary of Kawamata-Vivek.
I don't think so.
So that's independence.
Yeah, I think so, yes.
Sorry about that.
No problem.
Big pain, yes. Sorry.
It would imply Kawamata-Vivek when F is did it. Yeah. Okay, so now we're talking about topologically trivial line bundles. There are line bundles in this group. And so one important example is when A is an abelian variety, then we have a natural dual abelian variety, which is isomorphic to pick 0 of A. And on the product of these, I can consider what's known as the Poincaré line bundle. So P is the Poincaré line bundle. So what property does it have? It's sort of the universal line bundle for this modular problem. So let's sort of write down some of the properties. So first of all, I want to assume that P, when I restrict it to A times any point, let's say Y, so Y is any point in A hat, then this is going to be a topologically trivial line bundle. So sort of I'll denote it as P sub Y. This is the topologically trivial line bundle corresponding to the point y in a hat, right? So there's this isomorphism between the dual abelian variety and pick 0 of A. So any point in here prescribes for you a topologically trivial line bundle, and the Poincaré line bundle restricted to that slice is that topologically trivial line bundle. So it's a family of all of these. Now, of course, to uniquely specify this by the seesaw principle, I also need to tell you what the Poincaré line bundle does on a slice in the other direction. So we are also going to assume that if you take the Poincaré line bundle and restrict it to the origin on A times A hat, then this will be O of A hat. So this is the Poincaré line bundle. And the reason why I'm introducing it is that it plays an important role in generic vanishing terms. Maybe I should make one more remark just so that when X is a smooth complex projective variety, you should, well, you probably already know, but if you don't, you should know that you can identify pick 0 of X with pick 0 of A, and the map, of course, is for any line bundle in pick 0 of A, Py, you map it to the pullback of Py, and that's still a topologically trivial line bundle. But those two can be identified. Okay, so let me tell you about the cohomological support loci. So let's F be a coherent sheaf, say on X. Then the cohomological support loci of F is going to be the set of line bundles P in pick 0 of A such that the corresponding cohomology group does not vanish. Oops. Does not vanish. So a silly example is that the n of O of X is isomorphic to O of A. Why is that? Because you see we're asking for Hn of O of X. Okay, so here I've already abused notation. I should really be writing the pullback of P. So if you're asking for this to be non-zero, this group, the dimension of this group, is the same as, I got it wrong. I wanted to say omega x. Okay, so you'll see in a second. Okay, so this is isomorphic to H0 of O of A, so just A alpha star of P dual. So this is a topologically trivial line bundle. The only way it can have a section is if P dual is non-zero. Right, because these line bundles have degree 0, so if they have a section, then they have to be the trivial line bundle. It's the only way they can have a section. Okay, so that's just a silly example.
P dual is trivial? Like,
yeah. Thank you, thank you. And in fact, it's if and only if. Yes, perfect. Okay, so I could have phrased this as H0 of O of X, but you'll see in a second why I wanted to think of it as higher cohomology of the canonical bundle. Well, if you're in the frame mind of vanishing theorems, then you are in the frame mind of considering higher cohomologies of the canonical line bundle twisted by something. So stating it this way, so this is an easy example where you see that higher cohomologies of a line bundle of the canonical line bundle twisted by topologically trivial line bundle typically vanish, right? The only time they don't vanish is when P is the trivial line bundle. I guess it's bad to say 0. I should really say O of A to B. It's the origin in the dual abelian variety, but okay. So here's the theorem of Green and Lazarsfeld that gives you very precise information about loci of this form, but not just for the maximum dimension. So here's the theorem due to Green and Lazarsfeld. And I think it's 1987. So X is going to be a smooth complex projective variety. It actually also works for Kähler manifolds, but let me just stick to smooth complex projective varieties. And then it tells you several things. So first thing, if you look at these loci Vi of omega j of X, so this is the jth exterior power of holomorphic J forms on X. We're looking at the set of topologically trivial line bundles such that the corresponding cohomology group does not vanish. Maybe I should emphasize it. So the set of Hi omega j X tends to P different from 0. Then these are union of torsion translates of subtori of pic 0 of A. So this is contained in pic 0 of A, or if you want A hat, and it's a union of subtori. Okay, so a priori, this is just a closed subset of A hat, and we're saying that it has a very special structure. It's linear. It's just subtori. The second,
no translation.
Thank you very much. So when I said the union of linear subvarieties, that's the statement that you should be coming away with. Actually translates of subtori, and later on it was proven by Simpson that these, so this is not due to Green and Lazarsfeld, they actually translate by torsion points, which is a very important property. And I'll give you some idea at a certain point why it's translated by torsion points. Okay, and the second statement, so this is nothing about generic vanishing. It's just a statement about the structure of these loci. The second statement is what we call generic vanishing. So it's the codimension. So now I'm just going to look at Vi of omega x. So instead of taking, any holomorphic J forms, I'm thinking of the top level of the canonical line bundle. So if you want, you can think of this as omega n of x, where n is the dimension. Then, so the codimension, of course, inside of A hat is at least E as I minus n minus the dimension of A of x. Hopefully I got that right. So, okay, maybe I'll just call that dimension of x. So the nicest case is, e.g., if the dimension of x is equal to the dimension of A of x, then this says that the codimension of Vi of omega x is equal to n, is equal to I. So we've already seen one case where that's true. When you look at the highest one, it sort of has maximal codimension, right? The top cohomology of omega x, the corresponding cohomological locus has maximal codimension. It's just 1 point. If you were to look at Vn minus 1, it could be it could have dimension 1 and so on.
And a little bit. So subtori, they are of different dimensions?
Yes.
So when you say codimension of each torus? Or
Yeah, the codimension of the torus in the ambient variety, in this A hat.
So when you say like a codimension of Vi omega x, that means codimension of each torus.
Oh, so each component of this is a torus.
Yes.
And the codimension of each one of these tori in A hat is at least that much. So for example, if A is simple, so if you have a simple abelian variety, it has no interesting subtori, no interesting subabelian variety. So if A is simple and X is of maximal Albanese dimension, then this immediately tells you that Vi of omega X is equal to finitely many points. For any I greater than 0. Right? Because, why is that? It's each component is a proper subtorus. It's proper because of this codimension condition, and the simple abelian variety has no proper subtori, so they all have to be points. And in fact, the other consequence is if X has maximal Albanese dimension, then you see the Euler characteristic of omega X is the same as the Euler characteristic of omega X twisted by any topologically trivial line bundle P. But then this is the alternating sum of the dimensions of the corresponding cohomology groups. But now, since it has maximal Albanese dimension, the statement 2 says that for a general choice of P, that cohomology group is empty, right? So this is actually just equal to H0 of omega X tensor P, which is greater or equal to 0. So for a variety of maximal Albanese dimension, the Euler characteristic is always greater or equal to 0.
But in general, those subtori may have different dimensions?
Yes, sure. So, I mean, okay, so let's do a silly example. Similar to the one I wrote down before, but you asked for different dimensions, so let's arrange for different dimensions. So let's suppose that we have our abelian variety is going to be an elliptic curve, product of free elliptic curves. And then I want to arrange for, okay, so I'm going to fail at getting one example. Oh, maybe it's not too bad. So if I pick L1 ample, Li ample on each one of these, I can do these degree 2 covers. And so I could, okay, I'm going to make something that fails slightly from a point of view, but it will become clear how you should modify it. So then you could consider the cover which, so x to a z mod 2z squared cover with the property that the push forward of omega x will be of the form, of course, OA plus L1 box times let's say OE1 box times OE2 plus OE1 sorry 2 3 box times L2 box times L3 plus L1 box times L2 box times L3. Okay, so if you look at it this way, you know, it's a degree 4 cover. So the push forward of omega x, of course, these are all dual. I always forget to put that because I'm thinking of omega x. Okay, so the push forward, oh no, that's omega x. I got it right, sorry. So push forward of omega x, I'm expecting it to be a vector bundle of rank 4, right? And in fact, it's going to, since this Galois cover is going to split as a direct sum of 4 line bundles. These are the 4 line bundles. So now, when I go compute the loci, the cohomological support loci for x, it's the same as computing the cohomological support loci for this guy. Okay, so now we have the cohomological support loci for O of A. These are very easy, right? So there's 4 of them, V0, V1, V2, and V3. And what are they? They're just O of A for I equals 0, 1, 2, and 3. Right? Because you need to know something, and we'll prove something like this in a short while. But the cohomology of any topologically trivial line bundle, except for the trivial one, they're all trivial. In this case, it's very easy because I pick A to be the product of my free elliptic curve, so it's really advanced undergraduate exercise. Check this. Now, the next one is, if I look at this guy, Vi of L1, box times O E2, box times O of E3. Okay, so let's think about I equals 0. So this is the easiest one. We're looking for global sections. Whenever I twist by something non-trivial on the second or third factor, I'm going to kill all cohomology. So the only thing I'm allowed to do is twist by something non-trivial on the first factor. Since this is ample, whenever I twist by something non-trivial, it stays ample, so it retains sections. So for I equals 0, this is just going to be E1 times the origin times the origin. So it's going to be a one-dimensional component. For I equals 1, it will be the same thing because I'm going to have, for example, a contribution coming from H0 of this, which is non-zero, H1 of this, and H0 of that. For I equals 2, I'll get the same picture because I'll have a contribution coming from H1 of this, tensor H1 of that, so overall H2 of this product. And then for I equals 3, I get that it's actually empty. Because to get something in cohomology H3, I would need to have something in H1 of this, and this is ample. It's never going to happen. Okay, so that's the picture of this. So the loci have dimension 1 or codimension 2. And the interesting fact is, since this has codimension 2, then it has to sort of persist in two more degrees. This one had codimension 3, and it persists in 3 more degrees. So somehow there's some duality at work here. You may have seen similar statements with local duality of sheaves on a smooth variety, for example. The next one to look at would be this guy here. And when you look at that guy there, maybe I won't write it, but you'll get something similar. So this guy here, you'll get the i's, which look like, for I equals 0, since we have these 2 ample line bundles, we'll be allowed to twist by anything on E2 or on E3 and retain sections. So you get 0 times E2 times E3. For I equals 1, you'll get the same thing because you're just twisting by the non-trivial element of H1 of O of E1. But then for I equals 2 or 3, it will be empty. And again, here the codimension of this locus is 1. That's why it persists in 1 more degree. So it's an easy example, but it's sort of showing you that all kinds of different dimensions should come, but depending on what dimension you get in by V0, you're expecting the same component to appear in higher cohomologies as well. And eventually, we'll make that into a theorem. So it's good to have some examples. So now I need to make one last statement. So if X is of maximal Albanese dimension, so this is, sorry, in other words, maximal.
In this case, there's no translation.
Yes, so that's what I was saying. If you want to make it, so in particular, this one here is it's not contained in that one, so it's good for that. But there's no translation. Maybe you want to make it more interesting with a translation. You have to do a product with some other elliptic curves and add in some 2 torsion line bundles, and you can do that too. Okay, so going back to this one, if it's maximal Albanese dimension, then another interesting thing happens. V0 of omega x contains V1 of omega x. These may be equal all the way up to Vn of omega x. And this one is really small. This has to be O of x, O of A. Okay, so when it's maximal Albanese dimension, they're one contained in another.
Sorry, Christian, like that. You said the tori appear
what I said, they should be related. What I said so far is that if some tori appears in V0 with codimension I, then it should also appear in VI. The bigger the codimension, the further along there should be some echo of it.
I see. Thank you.
This is somewhat similar to what's the statement if you have a coherent sheaf which is locally free in a certain codimension. When you take the x, you expect something about where the x to i's live. It's a very similar statement to that, but it'll take a while till we get to that formulation. So what I wanted to do now was to give, so this is sort of the old school version of generic vanishing theorems, and I wanted to give you a quick intuitive proof of this, which can be made into a precise statement. Okay, so the first statement I want to address is why should you expect these to be subtori? Right? What's the reason? So, well, we can draw a very convincing picture, and then we'll have to say a few words to try and make it a little bit more convincing. So here's a hat. This is my best picture of the Beam variety. Then we have inside of a hat, we have some irreducible subvariety. So let's say that T is an irreducible component of Vi omega j x. Okay? So inside here, you have some irreducible component, I guess possibly singular. We know nothing about it. We just know that it's a closed subset. Okay? So now you pick a general point. You pick P in T general. So in particular, it's going to be a nice smooth point. And you look at the tangent space. Okay? So you look at the tangent space.
I'm sorry.
Go ahead.
Irreducible component, but I thought that was torus.
We need to prove that.
Oh, you're proving it. I'm sorry, because you wrote the thing, drew this.
Right. So this is the picture that never happens. So how do I prove that this never happens?
Sorry.
Right? So it should be a linear subvariety. It should not behave like that. So I pick a general point, and and the goal is show that the tangent space at P, and luckily I called this irreducible component T as well. 2T, I'll stick with that. Well, it's going to be a torus eventually, so might as well call it T, is contained in T. Okay, so if I can show this, if you have a subvariety of an invariant variety, and for a general point of the subvariety, it contains a tangent space, then it better be a linear subvariety, and it's going to be a subtorus, and this is the main thing I have to show. Okay, so how could you possibly go about showing this? So so this, we're thinking of this as H1 of O of A, quotiented out by H1 of AZ. And so I mentioned the tangent space, so let's pick a vector in the tangent space. So let's pick V is going to be an element of the tangent space at P to T. So I'm going to identify this with H1 of O of A, or if you want, with H1 of O of X. I can think of it, right, because those two spaces are isomorphic just by pulling back. So go ahead.
But this one is big. Contain. Tangent space and P of P. Yeah.
Certainly. Anyhow, I'm picking one vector. So no. It's good to try and correct as many mistakes as possible.
Sorry.
Okay, so I'm picking some vector in the tangent space, and I'm picking some element psi in Hi omega j x tensor P, right? And so since V is in the tangent space, I know that this section deforms to first order, right? So what I know is that psi deforms to first order in the direction v. Right? I mean, that's what it means for it to be in the tangent space, right? This is the space psi deforms along this subvariety T. Because it's a general point, so by semi-continuity, every section at a general point deforms nearby. It wouldn't be true for a special point, but for a general point, it's true. And by definition of tangent space, it means it deforms to first order in that direction. Okay, what I want is that psi deforms to all orders in this direction.
I'm not so sure if I understand what you mean by psi deforms to first order.
Well, I'm going to write a precise statement in a second, but so how can I say it? So this is sort of the modular space of all topologically trivial line bundles, and I can put them all together with a Poincaré line bundle, and so I can write some statement. You know, I can consider the product of X with this modular space, and I can consider.
But usually it's upper semi-continuous, no?
Yes, but at the generic point, it's constant.
Ah.
So yeah, so you expect it. If you push forward to the right thing, it should behave just like a vector bundle, something of locally constant rank, and so every section here should be deformed along the subvariety. So to first order, it just means that it's deforming along the tangent space.
Because I thought the special, but you're using the general point assumption.
Yes, I'm definitely using the general point, which I wrote down very quickly, but yes. And so in order to be able to prove something like this, you need to write down carefully what it means to deform to first order and what it means to deform to arbitrary order. Now, luckily, the situation is rather simple because the deformation theory of these topologically trivial line bundles is essentially governed by this exact sequence. So you can write down things very explicitly. I'm not going to go into all the details, but I'll show you the key part of the proof in a second. Before I do that, I need to give you a little piece of information about the main tool we use, which is Hodge theory. So Hodge theory, you're used to seeing Hodge theory without this P here, right? However, these line bundles P also admit Hodge theory. So they have admit unitary flat connection. So maybe it's sort of, you can think of these just like you can think of, you have a connection on O, and the locally constant sections are just the constant section C. Here you have a connection. The locally constant sections are no longer globally constant, but they are locally constant, and the global data is given by representation of pi1 in the unitary group. So this P corresponds to a representation from pi1 of A into U1, complex numbers of length 1. For any such representation, you get a locally constant system, and you can do Hodge theory on the locally constant system. Since it's with values in U1, complex conjugation gives you an isomorphism between P and P dual, which works just as complex conjugation on the constants. So maybe let me make some precise statements. Since P has a unitary flat connection, we can do particular, you have statements like H, under complex conjugation, you can identify HI omega J of X tensor P is complex conjugate to Hj omega I X tensor P dual. And, right, because when you take complex conjugation, it's like inverting your transition function, which is just given by a norm 1 scalar. And so we can talk about harmonic forms. And so everything from the usual Hodge theory holds, and in particular you also have the principle of 2 types, which I will use in a second. So we have the principle of 2 types. So what does it say? Suppose that I have some form in Hi omega J X tensor P, which is del bar P of psi is equal to 0, and it is, let's say, del exact. So it's closed for del bar, it's exact for del, then psi is del bar P del of some gamma. So, P there too. Okay, so if there was no P here, then it's the traditional principle of 2 types, and you can just develop the same exact Hodge theory.
Psi is DD bar?
Yeah, that would be a bit too good to be true. It's del bar or something, yes. So, so you just do Hodge theory in exactly the same way that you usually do it, except that the coefficients, instead of just being constants, the coefficients take values in this locally constant sheaf, where the transition functions are given by this representation into complex numbers of length 1.
Is C assumed to be harmonic?
Sorry?
Is this C assumed to be harmonic?
No.
No.
You don't have to assume it to be harmonic.
So just any form representing the homology.
As long as it's, well, it represents the cohomology, it's del bar closed, and it's del exact.
I see.
Okay, so if you're greatly offended by P, just pretend that P is the trivial line bundle. Then it's the usual Hodge theory. Okay, so now I need to tell you what it means. I won't do the detail, I'll just tell you what the outcome is. So what does it mean to deform your form psi to order T? So psi in Hj omega I x tensor P deforms to order, let's say, K, if we can solve the following. So if we can write psi plus psi 1 T plus psi 2 T squared, etc. And then we take del bar, I have to tell you in what direction, in the direction of V, we do del bar plus T wedge V, let's just call it TV of this, is equal to 0 modulo T to the K plus 1. Okay, so let's see what that means. Of course, I'm supposed to say with respect to the corresponding unitary system. Okay, so if I set K is equal to 0, I'm doing this modulo T, so I'm just requiring that del bar P of psi is equal to 0, right? So if, it's an element of that cohomology class, it represents an element of the cohomology class, so it better be a del bar closed holomorphic IJ, a del bar closed IJ form. Okay, so this is just saying that we have a class to begin with, right? The forms to order 0, we actually have the class. Okay, when k is equal to 1, what this says is, well, of course you have del bar p psi is equal to 0. This is the form that we started for. This is the initial data. But then we also have del bar p psi 1 is equal to minus v wedge psi. Okay, so let's interpret this for a second. So who is v? V is an element of H1 of O of A. We might as well assume that we choose this to be harmonic. Okay, so what do I have here? I have, okay, so this is a harmonic 0-1 form. So I have a 0-1 form wedged with an ij form. So it's an ij plus 1 form. This is del bar of an ij form, so at least they live in the same space. And what this equation says is, i.e., the class of v wedge c is equal to 0. So in cohomology, when I take the class of v and the class of psi, they wedge to 0. Right? I mean, this is 0 if and only if the corresponding ij plus 1 form is exact. That's all it's saying. Okay, so this is what it means to deform to first order. That's what I'm assuming. Now I want to show you that if it deforms to first order, it deforms to arbitrary order. So I already advertised the principle of two types, so I better use it. And look, I already have that this thing is, okay, so there's two ways of stating the principle of two types. Where was it? Here. You could ask that it's del bar closed, del exact, then it's del bar of something. But you could also ask that it's del closed, del bar exact, and the same conclusion holds. So, of course, I stated the dual one, but I think we can live with that. So, the principle of two types is going to tell me that then minus v wedge psi is of the form del bar p del p of gamma 1. And you're like, why is this helpful in any way? Well, we'll see. We'll use this information at the next round. So the next round is we want to show that we can deform it to second order.
Is that del bar?
Right here?
Yeah.
Well, if you switch them, I think it just changes the sign. So
sorry.
it's up to your preference.
No.
Which one you want to?
You're right.
Okay, so
Yes. Because you said you take a dual step, and I took the.
yes, and you're like trying to hold me to that, yeah.
Sorry, I'm always stupid.
No. So where was it? Okay, so now I want to show that we can deform into second order, right? So, and then if I end up with a similar thing, then we will know how induction works. Okay, so now to deform into second order, what I want to solve, I don't have it yet, del bar p psi 2 is minus v wedge psi 1. Okay? So, and I know that the way I'm going to succeed is if I can use the principle of two types again, right? So if I can deduce that this is del bar exact and del closed, then I use the principle of two types. Maybe del exact and del bar closed, I use the principle of two types and win. Okay, so let's see. So this is my dream. So what do I know about minus v wedge psi 1? Okay, so when I look at this, right, I can re-choose my psi 1 to be this guy. So psi 1 could be del p gamma 1. So this is going to be minus v wedge del of gamma 1. But now V was chosen to be harmonic, so this is minus. In particular, it's del closed, minus del of V wedge gamma 1. So we're halfway there, right? Because we've shown that this gadget here is del closed. Now I want to, it's del exact. Now I would like to show that it's del bar closed. So I really want to show that del bar of V wedge psi 1 is equal to 0. Now V is harmonic. So okay, that's what I want. I don't know that it's 0 yet. So this will be V wedge del bar psi 1, right? Because this one is harmonic. So when I sort of distribute this, I don't get any contribution from V. And now, what do I know about del bar of psi 1? So this is V wedge minus V wedge psi. But V wedge V is, of course, 0. So this is 0. So you put these two things together and the principle of two types, and you get that minus V wedge psi is of the form del bar P, del P of some gamma 2. And so we let psi 2 be this guy, and now formally we're in the same situation, so we can just repeat.
C1. No?
No, C2.
Minus B wedge C1.
No, I think I got it right this time.
Oh, I'm sorry.
So here I have a new gadget, which is del closed, del exact, del bar closed. So I apply for a second time principle of two types. So it's going to be del bar del of a new gadget gamma 2. And so I call this psi 2. Ah, this is what you were telling me.
Yeah.
You're right again. Very good, very good. Yes. Otherwise, it would be too similar to the previous one. You don't want it to be. Okay, and so you can repeat this process as many times as you want, and you show that it deforms to arbitrary order, and that gives you this expectation. I haven't done any of the details, but the details are not too hard. It gives you this expectation that this subvariety contains its tangent space, and so it has to be a linear subvariety.
Isn't this a proof?
You can make it into a proof, but okay. So why does deforming to arbitrary order mean this? You have to write down the transition functions for the Poincare line bundle, essentially. Right? So you have an exponential map. You're taking, I don't know, right? I mean, you have to write something down. It essentially is a proof, but
you take the generic point, P.
Yeah.
So the T may have a singularities.
No, because you see, if it's linear in the neighborhood of the generic point, then it actually has to be linear everywhere.
I see.
So you rule out the singularities. It's sort of course, you may have something like that, but then it's two irreducible components. Okay, so let me. So you notice that the next statements are just about omega x. So it's slightly easier to deal with omega x. You don't actually need the principle of two types because what kind of nice things happen for when you're talking about cohomology of omega x. First of all, when you're talking about cohomology of omega x, well, by saduality, you might as well be talking about cohomology of O of x. And by Hodge theory, you might as well be talking about cohomology of omega I of x. And you had your form in H1 of OX. So, right, and here the interesting thing was looking at HI omega x cup V to HI plus 1 of omega x. So if you apply saduality and Hodge theory, then you're going to end up looking at something like H 0 omega I plus 1 of omega of x, H 0 omega I of x, and here you'll be wedging. Yes, here you'll be wedging with omega, where omega is a complex conjugate to V, which is an element of H 0 omega 1 of X. Now you have this nice thing. So first of all, you know, if you're talking about something, if you have a form here, and you wedge with something in H0 of omega 1 of X, you can check whether this wedge is 0 non-zero locally, right? So let's call here an element phi in here. Phi wedge omega is 0. The class is 0. If and only if you pick harmonic representatives, that's 0 if and only if phi wedge omega is 0 on the nose. So a lot of the computations that you do become much simpler when you're talking about sheaves of global sections rather than hi of omega j. So I haven't proven anything. I'm just giving you a reason why the computations should be simpler in this case. So you don't actually have to resort to the principle of two types. You just end up talking about harmonic forms, and the result follows a bit easier. And in fact, you can be much. Yes.
H0 omega n minus I?
Yes. Okay. So I've done it slightly wrong. Thank you, because I'll need something like this later, so I might as well get them. So then here will be n minus I minus 1, n minus I, and the arrow goes that way. Yes, of course, you had the duality at a certain point, right? So the arrow should be inverted. Okay, so
Chris,
yes.
What were you saying there? You know, like you were saying you can replace this one with the principle of two types. What were you saying?
Oh, I'm just saying, the only thing I'm saying is that certain computations will simplify. And one of the reasons that they simplify, and we'll use this in a second, I think, is that if if you have two harmonic forms and you wedge them, their cohomology class is 0 if and only if their wedge is actually 0 on the nose. That kind of thing does not work in hi of omega j.
Oh, I see.
Right? So you need something fancier, principle of two types. Okay, so I made no mathematical statement really here. I just said it should be easier to deal with the case when we're talking about omega x.
Right.
In a second, I'll make a mathematical statement which tells you something even more precise than what we already said. So what do we have? So you have x times pick 0 of x, and you have, by abuse of notation, let me denote by p the pool.
Chris, it's okay. So now you're explaining number 2 or what?
Yes, I'm about to move on to number 2. But before I do that, I'm going to sort of explain a fancy version of number 1, essentially. Okay? So I'm going to write down a more precise statement about the infinitesimal deformations of the cohomology group. So what kind of more precise statement could you hope for? Well, maybe a sheaf theoretic statement. And so here's a nice sheaf. And what did we have? Well, we had a point and a tangent vector, right? So we're looking sort of a line in the tangent space. So let's pick here z. So z is some small ball, maybe even a formal neighborhood of the origin inside of the complex numbers. And, you know, maybe you want to think of z, or z could be spec of k, t, something like that. Okay, so now we're going to write the map corresponding to this point and the tangent direction. So this will be a map tau. So you want tau of, okay, so maybe we'll write it as identity times tau, and you want tau of t to be given by p plus tv. Okay, so here I'm being I'm mixing two different kinds of notation, right? So P, okay, maybe I should be slightly more precise. So you could think of pick 0 of A, you're identifying it with a hat. Here you have the line bundle P, let's say corresponding to a point Y, and Y is a point in A hat.
Expect T square or something?
Well, if you did T squared, modulo T squared, then that would be first order deformations.
Yes.
I want to consider arbitrary order deformation.
Oh, okay.
Right, so, and then quotient by T squared, you get first order. And here you have Y plus TV. So just the sort of this linear map into the abelian variety. So now here you can consider identity times T upper star of P. Just the restriction of the Poincaré line bundle to here. So what does this look like? It just looks like deforming your original topological triple line bundle Py in the direction of V. And then you could consider the projection onto Z. And now you can consider, you can try and compute RPZ lower star of the identity times T upper star of P. Right? Essentially, this is what we were trying to do, right? You're trying to...
Yeah, but I'm still unhappy when you write how P is equal to Y plus TV. This is just first order. Since you're, considering the map from spec of K, double bracket T.
Okay, so if you consider analytically an open ball of C around the origin.
And then you have infinite order expansion, no? Or
Yes, I want infinite order expansion.
yeah, so sorry, this bracket PV is not clear to me.
Oh, this one, well, now it's no longer a bracket once I use that isomorphism. So I need to give you a way for any value of T to associate a point of the dual abelian variety, right? So maybe there's an exponential map hidden somewhere here, right? Okay, so Y is a point in A hat.
Yeah.
So I really need this to be somehow something in A hat, right? And the way I've written it, it's not completely clear that it's something in A hat. So what do we have? We have H1 of O of A. This is something in H1 of O of A. And we map this to, am I getting, where's the exponential sequence? Yes. So we map this to H1.
Sorry, Chris.
Yeah.
How is a map of the spec, or are you thinking about the at the level of rings? So that's where my how T is equal to. I'm not so sure.
Okay, so forget about this description. Think of a analytic ball.
Okay.
Then this should make you happy. That's what I'm saying. In fact, in the original paper, it's just specified as.
Okay.
You can certainly do it in these terms, but maybe I have to be a little bit more careful about how I phrase things. Okay, so there's a precise statement that tells you how to compute these sheaves. And so we will compute these sheaves. The stalk at the origin of these sheaves will be given by the cohomology of a certain complex of a derivative complex. Let me get the notation straight. How do they call this? D dot P at 0. D dot P at 0. And so I need to tell you what this complex is, and maybe hopefully convince you that this identification is useful. So what you want to do is you want to consider harmonic forms on so the IP is given by let me do a fancy H, I of P, tensor O of Z. This should be the harmonic forms in A0I of P. So this symbol denotes harmonic forms in A0I of P. And then I need to tell you what the differential is. And so the differential is induced by, of course, by cut product with V, where V is a harmonic form in H1 of O of X.
So you pull back the Poincare bundle.
Right.
Take the push forward.
Right.
You're considering this one as a complex, and then you're taking the 0-degree part. Is that what the left-hand side is?
No. Okay. Forget about this. This is just saying that this picture is only accurate at the origin. It's the stalk at the origin. So this is stalk at 0, and under this map, 0 is getting identified with this topologically, the fixed P, right? So that's why the harmonic forms of P play a role, because that's what happens, right? So if we weren't varying, if we just quotient by T, then all we will get is cohomology of P.
R-I-P.
What is I?
R-I-P-Z.
Yes. Exactly. So if you really understand well the deformation theory of these cohomology groups, then you should also be able to understand the push forward of the sheaf. Right? That's measuring in a sheaf theoretic way how these cohomology groups deform, and that's what Green and Lazarsfeld do in their second paper on generic vanishing. So then the consequence of this is that one can compute this very explicitly, because now you're just looking at a complex and with specified differential. So then what you get here is you get the kernel of HIP V2 HI plus 1 P. So this you should think of it as tensored OZ mod the maximal ideal. Direct sum, the actual cohomology of the P dot. So the kernel modular the image tensored with the maximal ideal.
So this is a theorem, yes? This isomorphism.
Oh yeah. This is theorem due to Green and Lazarsfeld. So somehow this theorem should encode what we already know, plus hopefully some more, right? So it should, if I pick V to be tangent or not tangent, I should be able.
What is the statement?
Okay.
Kernel, what?
Okay, so this is my complex, right? So this complex here is tensored with O of Z, but the differentials are induced by cut product with V. When you compute this, what you get is in sort of, if I think of it as graded by T, in degree 0, I get the whole kernel. And maybe it's cut TV. In degree 0, I get the whole kernel. And in higher degrees, I just get the cohomology. Okay? That's what it's saying. So I'm going to illustrate it now. So Now we know that these loci T contained in V I of O of X, the way it's stated here. So you could,
when's the statement there? If the isomorphism holds, then you have the arrow.
okay, so if you can try and compute this cohomology. And the statement should be, it's not, I haven't stated it very well yet, okay? So roughly speaking, it should be that in degree 0, right, so this should be a module over O of Z. Okay, so if you quotient by T.
I'm sorry, like, are you describing this HI of dp dot? Is that what it is?
Yes, yes. I'm trying to describe the cohomology of this complex.
I see.
Okay.
Because I didn't know what this, so you're writing HI dp dot
Right.
is equal to.
So then computations, you should be able to compute that, hopefully.
Is equal to
Yes.
that plus.
Right, so there's going to be a term.
Yes.
So it's not just, I mean, your first guess could be, I see why, yes. Okay, so the kernel, I did write something wrong, and I must apologize. So it's a cohomology of just a regular thing, tensor with M. So what I'm trying to say is that in degree 0, you get something bigger than in higher degree. Right, so this is, I know you don't want me to think of it as a KT module, but let's pretend that it's a KT module. Then when you set T quotient by T, this is what you get, the kernel. When you look at the generic point, this is what you get, the actual cohomology. So you get something smaller. Okay, so that tells you that if you're deforming in a direction V that's not in the tangent space, then at the generic point, you should be getting 0 here, because the cohomology is going to vanish at the generic point. So if V is not in the tangent space at P to VI of O of X, then you get that the maps from HI minus 1 P cup V HI P HI plus 1 P is exact. If, on the other hand, the map is tangent, let me double check that I've written that statement correctly. Okay, so if I had written that statement correctly, the conclusion I should come from is that if I pick V to be tangent to my space, that should imply then these maps vanish. So these maps both vanish. Okay, so let's see if that matches what I've written down. So this statement is just the fact that then at the generic point, the cohomology is going to be 0 because it's not contained in this locus, and at the generic point, it's computed by this cohomology, so the sequence has to be exact. Now, if we're in the tangent direction, we have this space is potentially bigger than this, so it suddenly means that the image has to be 0. So why, so that explains why this map should be 0. So why does this map have to be 0? Well, if you're in the tangent direction, everything deforms to first order, and we know that this map is measuring what sections deform to first order. Everything deforms to first order, so this map is 0. So this map is 0 because everything deforms to first order in tangent direction. And this map is 0 because it's the only way for these two to match up, right? Otherwise, this equation is predicting a drop in the dimension. But if you're at the generic point of one of your components, the cohomology has to be the same.
So is that still kernel that looks like direct sum? So
yeah, I'm not claiming that this is as OZ algebras.
no, what's the claim there?
The claim is that if you quotient by t, this is what you get. So at the special point, this is the push forward.
Yes.
At the generic point, this is what you get. That's what the claim is. I don't remember exactly how it's written in green and light. Something similar to this, but maybe slightly more precise.
So therefore, hi of dp dot is equal to this direct sum.
As vector spaces, yeah. As C vector spaces, yes. And each graded piece will match up. And the only thing I'm using it is to tell you, that this is the value at the generic point. This is the rank of that sheaf at the generic point. This is the rank of the sheaf at the special point. If I'm going in a normal direction, the rank at the generic point has to be 0. It's just saying that this is exact. If I'm facing off in a tangent direction, then the two ranks have to match, at least for a generic P, and so I'm getting that this map is 0. Okay, so maybe I'll just show you how that implies these two statements, and then we'll stop. So here I've stated the statements in terms of cohomology groups with no canonical line bundle. You can do the same trick we did before. You can do surduality and complex conjugation, and you get H0 omega n minus I tensor P dual, H0 omega n minus I plus 1 tensor P dual. And similarly, this is wedging with a complex conjugate to V. So now, the statement that I have here, for example, is that certain groups are contained in certain others. So what I need to show you is that if this group is non-zero, then this group is non-zero, right? But that's easy to do, right? Because I made this remark that the wedge is non-zero if and only if it's actually non-zero as forms. So all I need to do is I need to convince you that I can pick a holomorphic one form that, given any form in here, I can pick a holomorphic one form that wedge with that form is non-zero. Okay? So what's the point here? X is of maximal Albanese dimension. So the map onto A might not be surjective, but it maps onto a subvariety of A, and it's generically a tau. So if I pick a general point here, then I'm getting an isomorphism between the tangent spaces. So now, if I have an n minus I form, and I is not equal to n, and I is not equal to 0, so if I have a form which is not a top-dimensional form, I can always pick a direction in the tangent space, in the cotangent space, that's skewed to that form, right? So at least locally, I can always do that. But you see, on an abelian variety, H0 omega 1 of A is generated. For any point, any cotangent form can be obtained by taking a global holomorphic one form. So I have a desired cotangent direction, which corresponds to a desired cotangent direction on A, which I can achieve with a global holomorphic one form. Just take that global holomorphic one form, pull it back, and wedge with omega is non-zero. So that says that if hn minus I is non-zero, then hn minus I plus 1 is non-zero. So it looks like the coefficient is going up, but you have to just view this as I plus 1 is minus I minus 1. So it's saying that if Vi is non-zero, then Vi minus 1 is non-zero. Okay, so it doesn't matter. You have to trace through the definition. We did some complex conjugation and things like that to decide if we, which direction the inclusions go. So this is the correct way. And we know that this has to be because we have examples. Well, this is always O of A, and we have example where this is not O of A. So it has to be this direction. If it's one. So then the question is, how do I get a codimension statement? Again, since I'm out of time, I don't want to keep you here too long, I just want to convince you that there should be a codimension statement, and then when you run the numbers correctly, this is the actual codimension you get. So we've just seen that if it's of maximal Albanese dimension, it's easy. The only way that this map will be 0 is if this form is sort of already contained in the span of the form that I'm considering here. Okay, but on the other hand, we know from this statement here that there are many forms. If you go in the tangent direction, the maps have to vanish. So the bigger the dimension, the more directions in which you have to vanish there are. Right? So the dimension of your Vi has something to do with how many wedges will give you 0. Right? Okay, so now think about the case of maximal Albanese dimension, so we don't have to worry about this relative dimension. I mean, this is just corresponds to the rank of the differential at the generic point. So it's easy to imagine how this comes into play. So you have phi in H0 omega n minus I tensor P. Then you see that phi wedge omega is non-zero for omega in a vector space of dimension at least I. Right? I mean, so think of the most stupid case. Think that phi is locally given by dx1 wedge dx n minus I. Well, then wedging by any of the remaining guys will give you something non-zero. Right? So you have at least that many forms that will wedge to something non-zero with this. Now, of course, this element phi is not necessarily a simple tensor, so there may be other stuff there. Right? So that's telling you that that's putting a bound on how much stuff wedges to 0. So you can play that off versus the dimension of the tangent space, and when you do that right, it gives you exactly this statement here. And it's sort of hinting that if you actually achieve equality here, then that phi should somehow be a simple tensor. So there should be some prescribed fibration or something.
Say it again.
It's hinting that if you get equality here, then the dimension of this vector space is exactly equal to I. You're expecting this guy here to behave like a simple tensor. So you're expecting there to be at least some kind of foliation, some kind of fibration maybe of X onto some smaller dimensional variety. Okay, so I'm going to leave it at that for now. This was, today was just motivation. I haven't really proven anything at all. I've given you well, I've given you a precise statement of Green and Lazarsfeld theorem. I've given you an idea of the techniques that go into the proof. And we've talked about the kind of results I want to discuss and about vanishing theorems. So next time, I'm going to leave all of this behind, and I'm going to give you a more modern take with complete proofs on generic vanishing and how it arises as a limit of actual vanishing theorems. So, so this was more motivation, and next time I'm going to start with formal proofs. So thank you very much.